Hello everyone, I am Karan Mashru. Welcome to this video. In this video, we are going to discuss solution of the problem of the day, that is perfect sum problem. First of all, let us start by understanding the question. What does question say? It says that given an array ARR of non-negative integers, it means that we have an array and the values will be integers and they will be non-negative. So all the values will be greater than equal to 0 and an integer sum. The task is to count all subsets of the given array with a sum equal to the given sum. So basically we are given an array which contains non-negative integers and we are also given one integer sum. So we need to tell how many subsets of this array are possible such that their sum, the sum of that subset is equal to this sum. Okay. Note, answer can be very large, so output answer modulo 10 to the power 9 plus 7. Okay, so if we look at the first example, we have n is equals to 6 and these are the 6 elements of the array and sum is equal to 10. So basically we need to tell how many subsets of this array are possible such that their sum is equals to 10. So output is 3. How? One subset is 2, 3, 5, their sum is 10. Another subset is 2 and 8, their sum is 10. And another subset is only 10 and its sum is also 10. So the number of such subsets whose sum is equals to 10 is 3. If we look at another example, then n equals to 5 and array elements are 1, 2, 3, 4, 5. Again the sum equals to 10 and the number of possible subset is 3. How? The sum of 1, 2, 3, 4. One such subset is this whose sum is 10. Another such subset is 1, 4, 5 whose sum is 10 and another such subset is 2, 3, 5 whose sum is 10. Okay, so these are the three possible subsets. So the output is 3. Complete the function perfect sum which takes n, that is the size of the array, and array, that is the array elements, and sum, that is the target sum which we want to achieve, as input parameters and returns an integer value. What will be this integer value? It will be the number of subsets of the given array such that their sum is equal to the given sum value. Okay, the expected time complexity is n cross sum and the expected auxiliary space is n cross sum, and the constraints are given here. N cross sum cannot exceed 10 to the power 6. So now if we think about solving this problem, then basically we need to tell the number of subsets of the given array such that their sum is equal to the given sum. So one of the possible ways, brute force approach, is to generate all the possible subsets of the given array and calculate the sum of each of the subsets. And for every subset whose sum is equal to the given sum, we will make a counter and increment it, right? So basically we can do this by recursion. So if I try to draw a recursion tree, suppose I call a function 6, 10, where 6 is nothing but the number of elements left to be considered and this 10 is the required sum. So basically I'll call a recursion function 6, 10, which will basically mean number of subsets of the first 6 elements such that their sum is equals to 10, right? Now what I'll do is I'll go at each element one by one from end to start, and for each element I have two choices, either to take that element and either not to take that element. So total number of subsets would be 2 to the power n, because for each element we have two choices. So now since here I am talking about the first 6 elements whose sum equals to 10, so now I will decide whether to take it or not to take it, because this is the 6th element. So there are two choices, either I take it or I do not take it. If I take it, then my remaining would be, number of remaining elements would be 5, first 5 elements, and remaining sum would be 5, because initially sum was 10 but I considered this in my subset. So now the remaining sum is 5, 10 minus 5 is 5. So what does this denote? Number of subsets of the first 5 elements whose sum is equals to 5, because I considered this element, and another option could be I do not consider this element in my subset. Then what would be the recursion called? Number of elements remaining to be considered are first 5 elements and sum will remain 10 only, because I do not consider this element. So basically this reads as number of subsets of first 6 elements whose sum is equals to 10 is equals to number of subsets of first 5 elements whose sum is equals to 5 plus number of subsets of the first 5 elements whose sum equals to 10. Here I considered the last element, here I did not consider the last element. Now I'll come to this, because here now I have 5, so I am considering the first 5 elements. So I'll decide whether to take it or not to take it. Again I have two choices, either to take it or not to take it. If I take it, then the remaining sum would be 2, and if I do not take it, the remaining sum would remain 5 only. Here also I'll either take it. If I take it, the remaining sum would be 7, and if I do not take it, the remaining sum would be 10 only. Okay. If I go further, suppose now this means that number of subsets whose sum is 7 considering the first 4 elements. So now I have to decide on this whether to take it or not to take it. Okay. So that is 2. Suppose I decide to take it. So number of subsets of the first 3 elements whose sum is 5 because I considered these elements, or I do not consider it. So number of subsets of first 3 elements whose sum is equals to 7. Okay. If I expand this, then here also I will be talking about 2. So either I consider it. So number of subsets of first 3 elements whose sum is equals to 3 because I considered 2. So now out of 5 minus 2, the remaining sum would be 3, or I do not consider it. So this will become 3 comma 5. Number of subsets of first 3 elements such that their sum is equals to 5. And in this way the whole recursion will be called, right? When will we stop? When the number of elements will become 0, right? And when the number of elements became 0, and if the sum is also equals to 0, exactly 0, then that would be one of my possible answers. So I'll increment my answer. How? So let me take this example. I have taken this example very intentionally. Okay. Here is a lot to understand. So how will I call this recursion function? So basically this is the given array and the sum I require is equals to 4. So out of the subsets possible of the first 3 elements, I want a sum of 4. So now I'll talk about the third element, right? Because here I have 3. So I'll consider it or not consider it. If I consider it, then the remaining would be number of subsets of the first 2 elements whose sum is 0. And if I do not consider it, number of subsets of the first 2 elements whose sum is 4. Now I'll decide on this whether to take it or not to take it. So if I take it, it would be 0 minus 0, 0. So it will become 1, 0. And if I do not take it, it will remain 0 only. Again here, if I do not consider it, it will remain 4 only, and if I consider it, it will remain 4 only because this is 0 and this will become 1. Okay, sorry. Now I am talking about this element. So either I decide to take it or I decide not to take it. This sum would remain 0 only, right? So this will become 0, 0, and this will also become 0, 0, right? Here number of remaining elements will become 0 and the number of remaining sum will become 4. And here also number of remaining elements will become 0 and the remaining sum will become 4. Okay. So now number of remaining elements is 0. So there is no further need to call the recursion. Now here the sum is 0. The remaining sum is 0. It means that this is one of the possible answers. This also gives me one of the possible answers. This also gives me one of the possible answers. And this also gives me one of the possible answers. So here I have considered the third element, not considered the second element, considered the second element, not considered the second element, considered the first element, not considered the first element, and so on. So these are the possible answers. So there would be 4 subsets. Which would be those 4 subsets? One would be 4 itself, another would be 4, 0, another would be 4, 0 because there are 2 zeros, one time this 0, one time this 0, and another would be 4, 0, 0. There are 4 possible subsets whose sum equals to 4. Okay. Now why I have taken this example? One thing to understand is in the question they have not said number of unique subsets. They have just said number of subsets, right? So if I have same number multiple times, for example 0, so this is the 0 at the, let's say this subset has the 0 at the first index and this has the 0 at the 0th index. So I will be considering these two as different, okay, different subsets, because I am not asked to calculate number of unique subsets. First thing. Second thing, when will we stop? When will we reach number of remaining elements 0? And at that time, if the remaining sum is also 0, then that is one of the possible answers and I'll increment my counter. Okay. So this is possible answer, this is possible answer. What does this denote? The remaining sum is 4 and the number of remaining elements is 0. So that cannot be considered as answer, because now if the remaining elements are 0, I cannot form a sum of 4. And similarly for all these. And even if it reaches negative, then that is also not possible, right? If at some point of time, if it became 0, minus 2. So what does that denote? That the elements which I have considered till now have value 2 more than the required sum. So initially it was required sum and I kept on considering different elements and it became minus 2. so that is also not considered. So basically all the leaf nodes when the remaining elements are 0, at that time if the remaining sum is exactly 0, then that is one of the possible answers and will increment the counter. Okay, so that's why I have taken this example. Now understand one thing, what would be the time complexity? Time complexity would be big O of 2 ki power n, because in recursion I'll be considering all the possible cases until I reach the remaining elements equal to 0, and the total number of cases are 2 ki power n. For each element I have two possibilities, either to consider it or not to consider it. So this will give us time limit exceeded. So we need to think of something efficient. Now understand one thing, the expected time complexity was n cross sum. So I want to reduce my time complexity from exponential to polynomial. So can I think of dynamic programming? I need to consider two things. Do I have here overlapping subproblems property? What does that say? It says that the same subproblems are called again and again in the recursion. Let us see. Here I have 3, 5, which denotes whether number of subsets whose sum is 5 considering the first 3 elements. Here also I have 3, 5. So the same subproblems are repeated. So we have overlapping subproblems property. Do we have optimal substructure property? It says that the solutions to the smaller problem are used for calculating the answers to the bigger problem. Yes, we have that also. Why? Because the number of subsets whose sum is 10 considering the first 6 elements is equals to number of subsets considering the first 5 elements whose sum is 5 plus number of subsets considering first 5 elements whose sum is 10. So we are counting the solutions to smaller subproblems and combining it to get the solution of the bigger subproblems. So we also have overlapping optimal substructure property. So both the properties we have here. So we can convert this recursion problem into a dynamic programming problem and convert the time complexity from exponential to polynomial. So now let's think of DP problem. So now if we think about dynamic programming approach, then let us solve this using the tabulation approach, right? So first of all, I need to think about the dynamic programming table or the DP table. So what would be its states and what would be its size? See, if we look at the recursion tree, then I have two parameters, one the remaining sum and the other the number of elements to be considered. So for example, what does this denote? This denotes number of subsets of the first 5 elements whose sum is equals to 10. Right? So I need number of remaining elements and the remaining sum. So can I take one DP table of size n plus 1 and sum plus 1, where DP of ij will denote number of subsets whose sum is equals to j considering the first I elements. Okay. So now first of all we'll fill the base cases for this table. So what would be the base cases? The first base case is when the number of remaining elements are 0 and the sum is greater than 0, we do not have any choices. So I can say for I equals to 1 to sum, dp of 0i equals to 0. So basically number of subsets whose sum is equals to I, where I ranges from 1 to sum, when 0 elements are considered, where 0 elements are remaining, is 0. Because if I do not have any elements, how can I get a sum? What is the another base case? The number of ways to get sum equals to 0 considering any number of elements is at least 1. Because even if I have 1 element, 2 element, 3 elements, there always exists one way to get sum 0. What is that? Empty subset. So can I say for I equals to 0 to n, dp of I0 equals to 1, number of ways to get sum equals to 0 using the first I elements is 1. So basically it is at least 1 because I can take empty subset that will give me sum equals to 0. Why I am saying it is at least 1? Because suppose I have this and I want to count number of ways to get sum 0. So one way is empty subset, another way is the first 0, another way is the second 0, and another way is to take both zeros, right? There are 4 possible ways, but there is at least one way. So I have filled the base cases. So now we have filled the base cases. Now let's fill the remaining table. So what we will do, for I equals to 1 to n, for j equals to 1 to sum. Okay. So basically at each step we are filling dp of ij now. Okay. So what does that denote? Number of subsets to reach sum j using the first I elements. Okay. Now understand one thing, when I am calculating dpij, before that, for all the values of I less than the current I and for all the values of j less than the current j are already calculated. So if I am, for example, calculating dp23, then dp of 1 3, dp of 2 2, all are previously calculated, right? So now I want to calculate this. So basically at this stage I'll decide whether to consider the ith element or not to consider the ith element in my subset. I have two choices, like I had two choices here, right? Now if I can only consider the ith element if its value is less than equal to j, because suppose my j is equals to 10 and if the value of the ith element is 12, so I want the sum j and the current element value is 12. So I cannot consider it anyway. So I will be putting a if condition to check this. Why? Because I do not want my indexes to go negative, right? So if array of I minus 1 is less than equal to j. So why array of I minus 1? Because I am running the loop from I equals to 1 to n, but the indexes would be 0 index. So I am taking I minus 1. Okay, that would be the ith element. So if its value is less than equal to j, I have two choices, either to consider it or not to consider it. So I can say dp of ij is equals to dp of I minus 1j. So this denotes, so dp of ij equals to dp of I minus 1j, that is number of subsets to reach sum j using the first I elements is equals to number of subsets to reach sum j using the first I minus 1 elements, that is this part. So I am not considering the ith element, plus if I consider the ith element, then it would be dp of I minus 1 and j minus array of I minus 1. So basically number of subsets to reach sum j using the first I elements is equals to number of subsets to reach the sum j using first I minus 1 elements, plus if I consider the ith element, then the remaining sum would be j minus array of I minus 1. So dp of I minus 1, j minus array of I minus 1. So basically this is equal to this plus this, right? So that is what I have done. The remaining elements would be I minus 1 and the sum, if I do not consider ith element, it would remain j. Otherwise it would be j minus array of I minus 1. But if else, that is if my current element has value greater than j, then I cannot consider it anyways, right? So dp of ij would be equal to dp of I minus 1 j. That is number of subsets to reach sum j using the first I elements is equal to number of subsets to reach sum j using the first I minus 1 elements. Okay, so in this way we will fill the whole table, and finally what will be written? We will return dp of n and sum, which is basically nothing but number of ways to reach sum equals to sum using the first n elements. Okay, so this would be our answer. Now let's look at its actual code. So if we look at the actual implementation, so I have taken one dp table of size n plus 1 cross sum plus 1, and I have taken mod value 10 to the power 9 plus 7 because we were told that the answer can be very large. So output modulo 10 to the power 9 plus 7. So I have initialized the base cases. What does this base case represents? If the number of remaining elements is 0 and if the remaining sum is greater than 0, then there are 0 possibilities. This is also the base case. If I want to achieve a sum of 0 using the first I elements, there is only one possibility, empty subset. So by default it would be 1. Okay, then I have filled the remaining table. Also please note that I have taken here j equals to 0 and not j equals to 1, right? During the concept part I told this j equals to 1, but it would start from j equals to 0. Why? Because as I said, there can be cases when we have 0 in the subset. So if this is the set, then to obtain some 0 we have 4 possibilities, 1 2 3 and 4. Okay, so here I said j equals to 1 to sum, but it would be actually j equals to 0 to sum. Okay, so this will be j equals to 0 to sum. If this element is less than equal to j, then as I explained, this would be this equation, but I have taken one modulo mod at the end, so the value does not exceed an overflow. And if that element's value is greater than j, then dp of ij equals to dp of I minus 1j, and finally we will return dp of n sum. What would be the time complexity? Time complexity would be big O of n cross sum, because that's the size of the for loops 1 to n and j equals to 0 to sum. And what would be the auxiliary space? The auxiliary space required here will also be big O of n cross sum. Why? Because this is the size of the DP table which we are taking, right? Now let's submit this code. So let's submit it. So we have solved this problem successfully. I hope you have understood this solution completely. Thank you.